Are we alone in this universe? Is there another intelligent species out there with the technology to reach us before we reach them? Have we already been visited by some alien species? Humans have been fascinated with these questions for thousands of years. That's why I thought it would be entertaining and informative to build linear models based on UFO sighting datasets to predict the number of UFO sightings in the future. In this video, we cover the following topics: analyze datasets, linearize datasets into functional models, interpret critical elements of the model, including slope, extrapolate using our model, and note any model breakdown. Hello, my name is Roy Simpson, professor of mathematics at Capstones River College in Sacramento, California. In this video, I'll review how to build a linear model given a data set and how to use that model to extrapolate information. So let's get started. This topic is known as a capstone topic. Not the UFO thing, but building linear models and using those to make predictions. For us, the word capstone means we'll use as much of our knowledge about linear equations as possible. If you can understand everything in this review video, and if you could have performed the mathematics here without my help, then you've mastered understanding of linear equations, linear models, and linear functions. The name of the game here is to squeeze as much mathematical knowledge as possible out of the problems that I'm going to present. The mathematics will be based on real-world information, so you can expect the arithmetic to be ugly. I will likely do what you should do when presented with ugly numbers. I'll grab a calculator. However, you should also know that you're responsible to be able to add two simple fractions if the numbers are not ugly. You will be asked to think critically. This is because you're in a transfer level math course and computations should be the least of your worries. You will want to ask yourself, is the data we're being presented with flawed? Is there an eventual breakdown to our model? Was the data cherry-picked to favor some argument? These should be questions that we continually think about while modeling data. Not how do you perform the order of operations or find the equation of a line. Those are old skills that you should have mastered by now. So let's get to the example. The National UFO Reporting Center has been collecting information on UFO sightings through their telephone hotline since 1974. What you see here is their actual data set. It lists the total number of reported UFO sightings. Let's take a subset of this data, say between 1965 and 1990, and create a scatter plot. Normally, with a smaller set of data, you would plot this by hand, but such a large data set begs for the use of a spreadsheet software, or in this case, Desmos. I'm just going to use Desmos here. Please note, when dealing with years as an input, you should set a benchmark year, like a 0 year. In this case, because we're only concerned with the data starting at 1965, I'll let 1965 be represented by x equals 0. That's a really common tactic in these problems. As a capstone problem for linear functions, you're expected to be able to build a linear model given data. As you can see, the data from 1965, which is x equals 0, all the way up to 1990, which is x equals 25, very loosely follows a linear pattern. In fact, you'd be correct in saying that it really doesn't follow a linear pattern. But let's build a linear model for this data anyway by selecting two good points and drawing a line between them. Before we get too far, we should clearly define what I mean by a linear model. In an algebra class, we're not too concerned with the line of best fit to a data set unless we're allowing some type of technology. The line of best fit, also known as a linear regression, is the one and only line that fits the given data set the best by essentially minimizing the distances between the line and the given data. That's a bit much for us here, so we do a more traditional method of just looking for two appropriate data points, such that when a line is drawn through them, it's a decent fit for the rest of the data.
Ouch.
Now, this video is not meant to teach you everything about linear models, so I'm not going to spend too long on the following statement, but beware the lies from scale. This is a common tactic used by media and bosses to scare you into thinking that you have to do something now to avoid disaster, or, as I can easily show you with our data set, scale can be used to make an illusion of pattern. These tricks should be well known to you, but beware that people make a living off of lying with data sets. What I've done here is shown a few possible choices. As you can see, there are some pretty decent choices for linear models matching the data set, and there are some pretty terrible choices. The process of selecting two good points for your linear model is completely heuristic. Let's use the green line as our model. It involves the data points at x equals 0 and x equals 25. Now let me be very clear, choosing the first and last point like this is not always the best, but in this situation, it looks like half the data lies above this line and half lies below, and it looks to follow the trend of the data, so I feel comfortable with this choice. Now I technically already computed the equations to showcase those lines. I'm going to redo it by hand here so you can see the work. From our prerequisite knowledge, we can build the linear equation using either point slope or the slope-intercept form of a line. I use the slope-intercept form of a line here just because I know that most people are taught to use the point slope form, and I like to be different, because I'd like to challenge your thought process during a review. You can always pause this video and try to figure out my steps. You might learn something new. I like to show you that there's more than one way to skin a Martian.
Oh, buggers.
That final fraction is going to be a bit of a pain in the end, so I'll make note of it. Fractional forms can be really useful when interpreting slope, but I'm going to convert it to a decimal right now. Because this is real-world data, the numbers and computations can get quite ugly. This is especially true if you choose other points within this data set. While we're at it, remember when I said that we would note any model breakdown? Well, here's our first encounter. When I showed the dataset on the screen, I did it so briefly that you may not have noticed that it went far beyond 1990. In fact, here's a slower look at that dataset. And here is a graph of the full dataset. Taking that into consideration, does it look like our linear model works well? Not in the long run. There are so many ways that you can be misled by someone who's shown you data, so just watch out. Another capstone skill is to flawlessly graph a linear equation by hand, even if you have decimals involved. Luckily, since we built the model using two of the data points in our given dataset, we can just plot those points and connect them with a line. The fact that this line is increasing agrees with our positive slope in our equation, and the fact that the vertical intercept is positive also agrees with our equation. Let's go ahead and graph this on the Desmo screen. One thing that I want to mention here: the graph of your linear model will contain, at the very minimum, the 2 points you use to build the model. It might not contain any other data points from the given dataset, or it might contain several other data points from the dataset, but it will always contain the 2 points you use to build the model. If you're not sure why this is true, please refer to the review video on creating linear models. A simple freebie question that you should be able to quickly handle is this one. We're just being asked to functionalize the model. This is a great Scrabble word, and I'm using it here in an alternative definition, but I hope you get the point. We just want to turn our linear model into a function. The process of doing this is pretty simple. Instead of x and y, we're just going to use t and s. T will represent the number of years since 1965, and s of t will represent the number of sightings that year. Turning a model into a function gives us power. Power to analyze, compose with other functions, do functional arithmetic with other functions, and evaluate the function using shifted time values or alternative time frames. All of that is the purview of a completely different video. This is a critical interpretation question, and there is no forgiveness in general if you don't know what to do here. The intercepts can easily be seen from your graph, and you can use your prerequisite algebra to quickly find them. In this case, the vertical intercept tells us that there were 226 UFO sightings in 1965. Remember that t equals 0 corresponds to 1965. The horizontal intercept is a little more interesting. Since the horizontal intercept occurs when the output variable s is 0, it tells us when there were no sightings. Solving this equation, we get that t is roughly equal to a negative 63.48, so roughly 63 to 64 years before 1965. So that's approximately 1901. Basically, in 1901, our model predicts there were no UFO sightings. This gives us yet another chance to view model breakdown. Our function shows that prior to the year 1901, there were negative UFO sightings. This is impossible. As I often say, a model is only good for a short time. Here's where showcasing understanding in a capstone problem for linear equations is critical. If you don't understand the meaning of the slope of your model, or if you don't even understand what slope is, you're definitely not ready for transfer level mathematics. And there is no offense intended with that statement. I'm passionate about this stance because whether you know it or not, slope is a critical concept necessary for calculus. Anyhow, slope, as we know, is rise over run, or change in output over change in input. And we can use that same concept to interpret the slope of this linear model. The unit for the rise, or the output, is the number of UFO sightings, and the unit for the run, or the input, is years. Thus, the unit for rise over run is UFO sightings per year. This is generally not a clear enough interpretation because if you just leave it at that, you're missing the numerical value of the slope. And that's half the meaning. Additionally, this capstone problem has a trick in it. Looking at our model, we see that the slope is 89 over 25, or 3.56. And so a lot of students would say that this means there are 3.56 UFO sightings per year. Remember, the rise is UFO sightings and the run is year. But that's just not true. Sure, a year might occur where there is that many or near to that many UFO sightings, but not all years had that many. Just look at those outputs. None of them are even close to 3. Nope. This is a wonderful example showcasing the need to include the words increasing or decreasing. A really good interpretation is that the number of UFO sightings is increasing by 3.56 per year.
Look, Mom, no hands!
Another interpretation is that each year the number of UFO sightings are going up by 3.56. Yet another interpretation, and one that uses the fractional form of the slope, is that for every 25 years, that denominator of the slope, the annual number of sightings increases by 89, the numerator of the slope. Each of these says the same thing in different ways, but none of them says we see 3.56 per year. When using a functional model to determine an output for a time that did not lie within our original dataset, we are performing extrapolation. That is, our original dataset went from time 0, which is 1965, all the way to actually 2018, which is time 53. In this question, we're asked for S of 65, where 65 means 65 years since 1965, or in other words, the year 2030. This year was not within our original dataset, so we use our function to extrapolate the number of UFO sightings in 2030. A simple computation using our function gives that S of 65 is roughly equal to 457. As mentioned earlier, this is likely not realistic because our model breaks down severely after 1990. And you can see that in the data. But what about the following question? Let's pretend that NASA recently stated that once the number of UFO sightings climbs above 5,000 per year, they will urge the government to go code red, whatever that means. And according to your model, we want to know, when will this happen? This is simply asking us to solve S of t is equal to 5,000. Doing so yields a time value of roughly 1,341. This is well over 1,000 years from now and really showcases how our model breaks down because according to the real world data, We already had 5,000 sightings in 2017 and actually several years around 2017. Well, thank you for watching this Capstone review video on predictions using linear models. As always, this content should be prerequisite to the course in which you're currently enrolled. If you found this material unfamiliar or if it was confusing to you, then I recommend you click on the provided relevant prerequisite links listed below for further help. However, if you find you're continually doing this, you might want to consider speaking to your instructor about other course options. On that note, I sincerely hope these videos help you achieve success in your transfer level math and science courses. Cue the music.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.